Welcome back to STEMLens. In the last video, we talked about pure substances, elements, and compound, whereby we classified elements into non-radioactive and radioactive elements based on natural radioactivity. We also classified elements into metals, non-metals, and metalloids based on their nature and properties. We also talked about compounds, combination of elements, where we discussed compounds based on their nature and properties to be divided into acid, bases, and salt. We also discussed and classified compounds that's based on their reaction with the atmosphere to be hygroscopic, deliquescent, and efflorescent. So in this video, we shall be talking about impure substances, which entails mixtures. Now, these are substances having the following features. Number one, the composition is indefinite. That is, consists of two or more elements and or compounds in any proportion by mass. Now when they say the composition is indefinite, that's the composition is not specific. It is not, it cannot, like for example, when you talk about something being definite, it could be the same, like it is constant. All right, it can be predicted. When you talk about composition being indefinite, it could be in any proportion by mass, not specific. All right. Now, number two, constituents retain their identities. That is, physical properties are retained. Now, it is a mixture. They are not chemically combined together, so they still retain their individual characteristics. All right. Constituents react differently to changed conditions. That's where separation comes in, whereby their reaction with different conditions can be used to separate them from each other. Alright, they can easily be separated into constituents by physical method. Alright, so mixtures can easily be separated because the constituents possess and retain their individual characteristics, so it is quite easy to separate them. Now it says many natural mixtures exist and several others can be formulated. Examples include air, the air we breathe, seawater, muddy water, palm wine, petroleum, alloys, and double salt. Okay, we have a table here showing mixtures and their major constituents. Of the air, we have gases to be nitrogen, oxygen, carbon, noble gases, water vapor. We also have pollutants or impurities, right? Hydrogen sulfide. We have carbon monoxide, gaseous lead. Okay, I jumped in. Okay, we have sulfur oxide, sulfur 2 oxide, gaseous lead, compound, sorry, poly. Right, we have seawater, we have muddy water, we have petroleum, organic compounds, mainly hydrocarbons, we have alloy, steel, and bronze. Metals to metal, alloy is combination of two, right? Or metal, non-metal, iron, carbon, copper, and tin. Double salt, we have simple salts to give us double salt. So these are examples of what mixtures. Right, as in elements and compounds, mixtures can be classified in several ways. Based on the number of phases coexisting, mixtures are classified into homogeneous and heterogeneous. Now, based on the number of phases, don't forget we talked about the phases of matter to be gas, liquid, and solid. Alright, so now homogeneous mixtures have their constituents existing in just one phase. So for instance, we have gas, liquid, solid. When it is gas to gas, liquid to liquid, solid to solid, the mixture is said to be what? Homogeneous. For example, gas to gas mixtures, we have air. Liquid to liquid, we have water kerosene mixture, water ethanol mixture. Solid to solid, we have alloys like bronze, etc., and powdered sulfur ion filling mixture. Okay, it says it should be noted that water and kerosene are immiscible. We'll talk about that when talking about the separation techniques. And so kerosene would be on top of water because being denser. When the two liquids are mixed, two layers are therefore obtained when water kerosene mixture is put into a separatory funnel. In contrast, water and ethanol are mixable liquid. Now, mixable means they can mix, just as the name sounds, alright, and dissolve in each other so that there is no layering when the two liquids are mixed. Secondly, we have heterogeneous mixtures. Now, these heterogeneous mixtures have their constituents existing in at least two different phases. They may also be subdivided into gas to liquid mixture, liquid to solid mixture, and gas to solid mixture. For the gas to liquid mixture, we have carbonated drinks, we have aerated drinks like beer and soft drinks. Liquid to solid, we have muddy water, we have sand, sugar solution. Gas to solid, we have harmattan, solid particles suspended in air. Now, that was based on the number of phases coexisting. That's we classified mixture into homogeneous and heterogeneous based on the number of phases coexisting. Now, we will also be classifying them based on the size of particles alright, whereby we have the solution, suspension, and colloids. Now, solutions are homogeneous mixtures of solutes and solvents. In a solution, the solute particles are distributed uniformly in the solvent. The solute is the substance, right? We are dealing with two keywords here: solution, right? Solute and solvent. Now, the solute is the substance that is dissolved to make the solution. Alright, that substance dissolved to make the solution is the word solute. It is usually present in smaller amount than the solvent, while the solvent is the dispersing substance that allows the solute to go into a solution. Now we are simply dealing with two different things here. What is being added to another? The solute is being added to the word solvent. Alright, the solvent most times could be liquid. Alright, the solvent is the dispersing substance that allows it receives the solute, alright, to form a solution. The solute could be liquid, gas, or solid. Also, the solvent could be solid or liquid or gas, but usually a liquid. Now, a solution in which the solvent is water is an aqueous solution. Most times, even when it comes to writing chemical equations, you always see in a bracket, lowercase, you see AQ. That means aqueous, alright? And aqueous simply means water is involved, alright? It is a solution in which the solvent is a water, is water, alright? Now, solutions have the following properties. Number one, the size of the particles is small or less than or equal to 10 to the power minus 8 meter in diameter. For water solution, they do not settle on standing. They pass through ordinary filter papers. They pass through permeable membranes. The particles are not visible with microscope or naked eye. They are clear and may have color. They do not exhibit light scattering, known as the needle effect. Alright, so solutions are let's just put it that solutions are pure mixtures. Alright, mixtures are impure, we all know, but let's just say solutions are what? Pure mixtures. Now, suspensions are mixtures of small insoluble particles of a solid in a liquid or gas. Examples include powder chalk in water, muddy water, harmattan. Suspensions have the following properties. Number one, the size of the particle dispersed is large. Don't forget, in solutions, the size of the particle is small, probably around 10 raised to the power minus 8. Alright, but now in suspensions, we have 10 raised to the power minus 5 to 10 raised to the power minus 4 meter in diameter. Alright, so the particles settle on standing. That's when they are being centrifugated, for example, or even when they are being left to cool down. They settle on standing. They do not pass through ordinary filter papers. You can easily filter them. For example, when you mix sand and water, you can easily filter it. Alright, the particles do not pass through permeable membranes. Sure, they could not pass through a filter paper. Do you think they'll be able to pass through permeable membranes? The particles are visible with microscope or naked eye. Exactly, they are cloudy and may have opaque color. They scatter light, that's the exhibit needle effect. They do not show Brownian movements following random zigzag path. Alright, so that's for suspension. Now, lastly, talking about colloids. Colloids are homogeneous mixtures of two phases, the dispersed phase and the dispersion medium. The dispersed phase is analogous to the solute of the true solution, while the dispersion medium is analogous to the solvent. Alright, so we are just trying to, form an analogy whereby we are linking colloids to what? Solutions. The dispersed phase is analogous to the solute. Alright, while the dispersion medium is analogous to the solvent. Examples of colloids include starch in boiling water, emulsions, foam, gel, and salts. The particles, the properties now. The particles are larger than those found in a solution but smaller than those in a suspension. They range between 10 to the power minus 6 to 10 to the power minus 8 in diameter. The particles do not settle on standing. The particles pass through ordinary filter paper. They do not pass through permeable membranes. The particles are visible in ultramicroscope. They may be clear or cloudy. They may have color. They exhibit neither effect. They show Brownian movement. Now, this colloids, for example, whereby we have pap. When you look at your pap, you will not be able to easily identify that, oh, there are some undissolved solvents, undissolved solutes, in this mixture. But with the help of a microscope, you can see that they scatter light, right? So they are colloids. We have a table here showing different, colloids. Number one, we have foam ladder, whereby we have gas dispersed in liquid. Gas dispersed in solid, we have charcoal. Liquid dispersed in gas, we have mist cloud. Liquid to liquid, we have emulsion. Liquid to solid, you have paste, gel, sol. Solid to gas, we have smoke. Solid to liquid, we have milk. Solid to solid, we have gold bearing rock. Alright, so mixtures are usually separated into their constituents by physical processes, mainly although chemical processes may be involved at times. The principle of separation is based on differences in physical properties or chemical reactivity of the constituents of the mixture. These properties include number one, we have about 9 of them here. Number one, state of matter or the phase involved. Number two, solubility in water or other solvent. Number three, migration of an absorbent. Number four, magnetizability. Number five, boiling point of volatility. Number six, size of particles dispersed. Number seven, mixability of liquid. Number 8, we have density, and lastly we have reactivity. That's a chemical method. Alright, so the separation technique based on the above principles include evaporation, distillation, chromatography, sublimation, filtration, centrifugation. Lastly we have precipitation. Alright, there's a table for that. We're going to look at a table, but let's just take these examples, about 3 of them. Okay, it says more often than not, 2 or more techniques are combined in the course of separation of mixtures or purification of substances. Example 1, we have resolution of sugar sand mixture. Add water to the mixture, shake vigorously. Sugar dissolves to form a solution while sand does not. Right, you can see that they are acting independently. Alright, sand is the residue upon filtration. Sand is the residue while sugar solution is the filtrate. That sand remains. Alright, while the filtrate is what? Sugar solution. You evaporate the filtrate to dryness by heating. So the techniques used are filtration and evaporation. We have resolution of ammonium chloride, sodium chloride, and barium tetraoxosulfate mixture. Alright, here you heat the mixture. The ammonium chloride sublimes. Alright, sublimation, that it goes into the gas phase spontaneously, like not spontaneously, but it goes without passing through the liquid phase, and can be collected in a cold inverted funnel. Alright, add water to the residue left and stir well. Filter. Barium tetraoxosulfate 6 is the residue while sodium chloride solution is the filtrate. Evaporate the filtrate to dryness by heating. The separation methods used here are sublimation, filtration, evaporation. And lastly, resolution of a mixture of finely divided solid material in a liquid. This is just an example of suspension. So centrifugation, decantation, or just filtration would work very well. Alright, so this is the table. Now I want to look at the table. This table is showing separation and purification techniques and the principles involved. It is very important to know the principles involved so that you can know how to apply them when necessary. Number one, we have evaporation and heating. It is based on the relative volatility of solute and solvent. For example, there we had, in number one, whereby we had a resolution of sugar and sand mixture. Alright, so we could just heat the sugar solution, the water evaporates and leaves the sugar for us. Number two, we have distillation difference, boiling point difference between constituents, liquid, that's simple or fractional distillation. Okay, we could use that probably in the production of fuels and all that. We have filtration or sieving. This is based on the relative size of particles running through a porous medium. Right, for example, you sieve a lot. When you pick sand, you want to maybe you want to separate the clear sand from the stones. You want to, like in the beach, they do it a lot in the beach. A lot of people may come and introduce stones, so they may once in a while filter or sieve the beach sand. Alright, we have chromatography, relative migration of constituents of mixture over an absorbent, or value difference of constituents of mixture. We have crystallization. This is based on the relative solubility of constituents at low and high pressures. We have sublimation or heating. Alright, this is based on the relative volatility of constituents of solid mixture upon heating. Alright, for example, in the first example where we talked about ammonium chloride as well. Alright, so the ammonium chloride, alright, let me go back there. We talked about ammonium chloride. So the ammonium chloride sublimed, alright, and was collected in a cold inverted funnel. Alright, so that's an example of sublimation. You can see that it was based on, because ammonium chloride boils, it has a high volatility, alright, a low boiling point. Now, use of separatory funnel, we have density and mixability of constituents of liquid mixtures. Right, I mentioned it earlier. Use of separatory funnels, for example, when you mix water with kerosene being denser will be at the top. Alright, so in a separatory funnel, you can just easily open the tap at the down, filter the water, and then you take your kerosene. We have centrifugation. This is based on the relative settling of light particles when solid liquid mixtures are subjected to a circular motion in a centrifuge or ultracentrifuge. This is just something that spins it. It spins. If you see the picture, it looks like a spin. Alright, so upon activation, it spins, goes very fast, such that most of the particles settle. Alright, they settle, they stand. Alright, we also have decantation. It is similar to centrifugation. This is based on the phase difference between the settled solid particles and the supernatant liquid on top. Right, that's it. Precipitation we have based on formation of water in soluble compound or mixing to aqueous solutions. For example, if you mix simple salts, you may get some precipitates. We have trapping. Constituents of mixture react differently to chemical substances. Hence, a constituent may be trapped or absorbed by a chemical substance, while other constituents are unaffected. Alright, you can see that, for example, in our first example, the sugar dissolved in the water while the sand was still on its own. Right, that could be an example of trapping. We have solvent extraction, partitioning of a substance between two immiscible solvents. Lastly, we have magnetization. That's based on relative magnetizability of constituents of solid mixtures. Alright, so that's all about, those are the separation techniques, and we just discussed the principles involved. So in the next video, we'll dive deeper, exploring examples. Alright, thank you so much for joining today's video. See you next time.